Hi everybody, today we are going to talk about some of the geometric applications of cross products. So some of these applications we have talked about before, mainly the fact that the cross product of u and v yields a vector that is orthogonal to both u and v. But there are many other useful applications of the cross product. One that we're really going to focus on today is this one at the bottom, number 4. So this one says that the magnitude of the cross product of vectors u and v will yield the area of a parallelogram as long as u and v are adjacent sides of your parallelogram. So this can be really, really useful in our geometry application-based problems. So let's give this first one a try. The first thing they would like us to do is show that ABCD is a parallelogram, given these 4 points, and then we're going to find the area. So the first important thing to know is how do we prove that something is a parallelogram? So one of the main definitions of a parallelogram is that both pairs of opposite sides are parallel. So if we can show that both pairs of opposite sides of ABCD are parallel, we can show that it is a parallelogram. So we really don't even have to sketch out a graph to be able to determine which vectors would represent the opposite sides. So let's say we have, something that looks like this. Let's call this A, B, C, and D. Regardless of the orientation of A, B, C, and D and where they are relative to each other, this vector, AB or vector BA, doesn't matter which one you use, is going to be opposite of this vector, and this vector will be opposite to this vector. So we're going to need to find the component forms of all 4 vectors and compare them to their opposite sides to make sure they're parallel. So remember, how do we determine if 2 vectors are parallel? They are parallel if the component vectors are scalar multiples. So that's what we will be looking for. Okay, so we're going to compare vectors AB and DC. And it doesn't matter if you use AB or BA. In the same way, it doesn't matter if you use DC or CD. Your component vectors might look a little different than mine. They would be opposites, but you should still be able to reach the same conclusion. And then after that, we are going to compare the other 2 opposite sides. So vector AD and vector BC or CB. So let's start by creating the component form of vector AB. So B is our terminal point. So we have 2 minus 5 is -3, 6 minus 2 is 4, and 1 minus 0 is 1. And now let's find the component form of vector DC. I'm using C as the terminal point. So 2 minus 5 is -3, 4 minus 0 is 4, and 7 minus 6 is 1. So if we compare these 2 component vectors, we see that they actually are scalar multiples, and that scalar is just 1. So since we've shown that they're scalar multiples, we've concluded that vector AB is parallel to vector DC. However, this is not enough to show that this is a parallelogram. We have to show that both pairs of opposite sides are parallel. So let's compare, let's first mark what we just showed. We showed that AB is parallel to DC. Now we need to check these 2 vectors. So let's find the component vector of AD. So I'm using D as my terminal point. So 5 minus 5 is 0, 0 minus 2 is -2, and 6 minus 0 is 6. And now for BC, I'm using C as my terminal point. 2 minus 2 is 0, 4 minus 2 is 4 minus 6 is -2, 7 minus 1 is 6. So once again, we have shown that AD and BC are scalar multiples, and that allows us to conclude that the 2 vectors are parallel. So now that we have shown that both pairs of opposite sides are parallel, we have proven or verified that D is a parallelogram. So now we are able to find the area using our formula, that the magnitude of the cross product of any two adjacent sides will be the area. So you can pick whichever ones you want. It doesn't matter. Let's say as long as they are adjacent. So let's use AB and BC. And it also doesn't matter the order that you do it in. You should end up ultimately with the same area. So let's find the cross product of AB and BC, our two adjacent sides. So let's set up our 3x3 matrix so we can find the determinant. So we start with I, J, and K. For AB, we're going to use these coefficients. And for BC, we have our coefficients right here. And let's use the diagonal method to find this determinant. Okay, so here our cross product will be 24i plus 0k, or plus 0j minus 6k, minus 0k minus 2i minus 18j. So our cross product is going to be 26i plus 18j minus 6k. So now to finish finding the area of this parallelogram, we're going to take the magnitude of this cross product, which will be the square root of 26 squared plus 18 squared plus negative 6 squared, which will be the square root of 1036, and we can get a decimal approximation for that. So our area is going to be approximately 32.19, and we'll say units squared. There you have it. So remember, first you need to prove that the quadrilateral is a parallelogram by showing that both pairs of opposite sides are parallel. From there, once you've proven that it's a parallelogram, you can take the magnitude of the cross product, and that should yield the area of your parallelogram. All right, go ahead and pause the video and give this one a try. All right, so go ahead and check your work. First, make sure you have successfully shown that ABCD is a parallelogram. Then you can check your cross product. Depending on how you wrote your vectors, yours might be opposite of mine or slightly different, but you should ultimately end up with the same answer once you take the magnitude of that cross product. So either 2 root 21 or decimal approximation of 9.17 units squared. Okay, so now we're going to try finding the area of the triangle with the following vertices. So maybe you're thinking, well, why are we moving on to triangles? We only know the area of a parallelogram. Well, luckily, a triangle is just half of a parallelogram. So let's imagine we have something like triangle ABC, however it looks. So we can find the area of this triangle by essentially creating a parallelogram, finding the area of that, and then cutting it in half. And actually, we don't even have to find the other vectors to make the parallelogram. We just have to pick two adjacent sides. So we could create a parallelogram that looks like this, and we could use CB and BA as our adjacent sides. Or we could, for instance, make a parallelogram that looks like this. And we could use CA and AB as our adjacent sides. And you should end up with the same exact answer. So it really doesn't matter how you frame your parallelogram. So let's imagine we have one like this. Now, we actually don't even need to figure out what this coordinate is, because for our formula, all we need to do is find the magnitude of the cross product of two adjacent sides. And we have the two adjacent sides. So we're going to use CB and BA as our adjacent sides. We don't have to prove that these are parallel because we're not even using this vector. We don't have to prove that these are parallel because we're not using this vector. We're just assuming that there is a parallelogram here, and we're going to cut that area in half to find the area of our triangle. So let's start by making the component form of vector CB. So B is our terminal point. So 5 minus 4 is 1, 4 minus 1 is 3, 6 minus 5 is 1. So that is vector CB. And now we need vector AB, our other adjacent side of our imaginary parallelogram. So A is going to be our terminal side. 4 minus 5 is negative 1, 3 minus 4 is negative 1, 0 minus 6 is negative 6. So from here, let's find the cross product. So I'm going to set up my matrix, and we have 1, 3, 1, negative 1, negative 1, negative 6. And I'm going to use the diagonal method. Okay, so our cross product here should be negative 18i minus j minus k minus negative 3k minus I minus 6j. So this should yield the cross products. We have negative 18 plus 1, so negative 17i. And then we have negative j plus 6j, so plus 5j. And then we have negative k plus 3k, so plus 2k. So this is our new vector, and now we're going to find the magnitude of that vector. So the magnitude of the cross product should be negative 17 squared plus 5 squared plus 2 squared, which gives us the square root of 318. And since it's the area of a triangle, the triangle's half of the parallelogram. So 1/2 times the square root of 318. And we can get a decimal approximation for that as well. It's going to be 8.9 units squared. There you go. All right, go ahead and pause the video and give this one a try. Okay, so here you can see that I picked the adjacent sides AB and BC. I found the cross product, which I got right here. Depending on how you named your vectors or which two adjacent sides you chose to use, you might have a slightly different answer here or even here, but by the time you take the magnitude to find the area, you should end up with that same answer. So it doesn't even matter how you set it up. So once you divide that in half, your area should be 6.6 units squared. Okay, the last thing we're going to do is talk about a new concept, which is called the triple scalar product. So this is if you have 3 vectors, vector u, vector v, and vector w. The triple scalar product, which you write like this, you can see it's actually a dot product and a cross product, can be found by taking the determinant of the 3 by 3 matrix that's created by using the coefficients of u, the coefficients of v, and the coefficients of w. So since we no longer have that I, j, k, those standard unit vectors, the triple scalar product is going to yield a value, not a vector. So it is different from the cross product alone. But it's really easy to find. It's just another 3 by 3 matrix determinant. That's all. So the triple scalar product is really useful application-wise to find the volume of what's called a parallelepiped. So a parallelepiped is essentially, it's like a cube, but instead of the sides being squares, all of the sides are parallelograms. So this is what a parallelepiped looks like. So as long as your 3 vectors, vectors u, v, and w, are adjacent edges of your parallelepiped, you can find the volume of this figure by taking the triple scalar product of vectors u, v, and w. And then it's going to be the absolute value of that of your result, because volume has to be positive. So it's super easy to do as long as you know this really cool formula for the triple scalar product. All right, so let's look at this first one. So here you can see that we have a parallelepiped, and we are given 3 adjacent vectors. And these are really nice vectors too, because they're actually all component vectors. Their initial point is at 0, 0, 0. So we can write the standard unit form of these vectors. So vector u, which you can see is right here, is simply 3i minus 5j plus k. Vector v, you can see, is right here. Should be 2j minus 2k, and vector w is 3i plus j plus k. So now, since we have the vectors for 3 adjacent edges of our parallelepiped, we can find the volume by taking the absolute value of the triple scalar product of u, v, and w. So let's do that. All we have to do is set up our 3 by 3 matrix using the coefficients first of u, then v, and then w. So I'm going to take this determinant using the diagonal method again. So here, let's see, we have 6 plus 30 plus 0 minus 6 plus 0. So this gives us 36. From here, we know that the volume is the absolute value of that, which is just 36. And then we can say units cubed because it is volume. And that's all there is to this problem. So I think these definitely look a little bit intimidating and it looks scary, but it's really, at the end of the day, just finding the determinant of yet another 3 by 3 matrix. All right, go ahead and pause the video and give this last one a try. Okay, so here you have the triple cross product of vectors u, v, and w. It should yield a value of negative 15, so the volume is the absolute value of that, so 15 units cubed. All right, that is all for today. Thank you so much for watching.